This video is a sample physics problem in one-dimensional motion. We have a sports car that starts from rest. It reaches a speed of 60 miles per hour in 3 seconds and is moving in a straight line towards the west. The first thing to calculate the average acceleration in metric units, and then find out how many quote-unquote G's this is by dividing by 9.81. Compute the displacement of the car after 2 seconds. Where is it? And think about the numbers. Is there anything unrealistic about the calculation? Then calculate the velocity of the car at a time of 1.6 seconds and at a time of 30 seconds. Is there anything unrealistic about this calculation? So it is good to make a little sketch, a little drawing of the situation. So just a simple one here on the bottom here, headed towards the west, reached 60 miles an hour after 3 seconds. So what's our average acceleration? Well, average acceleration is the change in the velocity divided by the total time required to make that change. This is a situation over a time period, so we're getting an average number. It's not instantaneous acceleration. It's not the acceleration at one instant of time. It's an average because we're dividing by some span of time. Well, the first thing I'd like to do is convert to more standard metric units. 60 miles per hour. There are 1,609 meters in a mile, so the miles units will cancel. And then 1 hour is 3,600 seconds, so the hours will be canceled off. And you could pause the video and do this calculation to verify. 26.82 meters per second. Well, we started with 0 meters per second. We started from rest. Now we're at 26.82 meters per second to the west, so you divide by 3. 8.94 meters per second squared to the west is the average acceleration. What about the feel of this? How many G's is the driver or passenger in the car experiencing? Well, to get that number, we just divide by the acceleration of gravity magnitude, 9.81 meters per second squared, and we find that the number of G's is 0.911 G's. It's a little less than 1 full G, and we don't need the direction here, but it is to the west. How about the displacement after 2 seconds of motion? We're dealing with constant acceleration here. We're assuming constant acceleration. So the first kinematic equation will help us find the final velocity. Vx equals Vx naught, the initial velocity, plus the acceleration multiplied by the time. In this problem, we're starting from rest, so Vx naught is 0. And Vx, the final velocity, is 0 plus 8.94 meters per second squared times 2 seconds. So the final velocity is 17.88 meters per second. So the displacement, the position can be calculated then. The x minus x naught. X is the final position. X naught is our starting position, and we'll let that be 0. So 0.5 times Vx plus Vx naught multiplied by time. This is a second kinematic equation. So we'll put in the numbers we know. The Vx is 17.88. Vx naught is a 0. And we've asked for the displacement at 2 seconds. So we get x minus x naught is 17.9 meters to the west. Is there another way to do the calculation? Well, yes, there is. There's a third kinematic equation that can give us the answer. Final position minus initial position equals initial velocity multiplied by time plus 0.5 times the acceleration times t squared. And we know these values, so v naught is 0. Acceleration is 8.94 meters per second squared for its magnitude. And again, pause it, work out the calculation on your calculator, and hopefully you'll come up with 17.9 meters. Why do I say this is to the west? 17.9 meters to the west. Well, the acceleration, we're told this car is moving in a straight line towards the west, and it's picking up speed, but it's moving to the west. This is a one-dimensional problem. It's not going north or south at all, just to the west. Is there anything unrealistic about the calculation of this for a sports car? Well, the kinematic equations only can be used when the acceleration is constant. Cars don't have constant acceleration. Your transmission is changing gears, you're changing speed in various ways. So no, it's not a real world calculation, it's an approximation. And we have an average acceleration. We don't have the acceleration at any one instant in time, but it is a little bit of an approximation, unrealistic, because the acceleration is not constant. But in an introductory physics course, to do the problem, we need to assume constant acceleration. What about the velocity? Let's calculate the velocity at 1.6 seconds and at 30 seconds. The 1.6 second number is inside this 3 second number. The 30 seconds, oh, that's quite a ways into the motion. Let's see what happens. Well, we might think to use the first kinematic equation. Final velocity equals initial velocity plus acceleration multiplied by time. If we do this for the 1.6 second case, again, you can pause the video and verify this. I got 14.3 meters per second. For the case of 30 seconds, multiplied by this assumed constant acceleration, we came up 268 meters per second. Anything unrealistic about these numbers? You may not be familiar with meters per second, so let's change them to miles per hour. And also, again, the acceleration is not constant, but there's a bigger problem. For this first result, the final velocity of 14.3 meters per second, at the time of 1.6 seconds, we get 32 miles an hour. That's not unreasonable for a sports car. But the other calculation, at the 30 second, assuming constant acceleration, that 268 meters per second becomes 600 miles per hour. That is unrealistic for a sports car. And the problem is the way I pick these times, 1.6 seconds is really inside the data, from 0 seconds up to 3 seconds. 30 seconds is way outside the data, an extrapolation, and that can lead to problems. So think about the numbers as you do physics calculations. The mathematics doesn't always give you a reasonable result. Apply your brain. So website gpclements.com, the website I have that I list all the YouTube videos that I've posted. You'll find there a description of the video, its title, a direct link to the YouTube video. It tells you how many minutes the video goes and gives you a little description of the video. All this content on this website is free. My videos are free. You're not allowed to resell them. At the website, you don't have to register. You don't have to give your email address. You don't have to give your name. You don't give me any information. And my website does not put cookies onto your computer. So keep working physics problems and improve your skill at problem solving.